very much. Great being here. Honored to be on the same stage as these cool astronauts here on Monday and Tuesday. That was quite inspirational to see a man who actually walked on the moon talk here. It was quite an inspiration, I must say. So thanks for the opportunity to give you a brief overview and a presentation of really applying commercial best practices to aerospace applications from a vendor's perspective. So Cadence, you may wonder who the hell is Cadence? So we are a vendor in this space, and I'll tell you a little bit more about what we're doing, which is an enablement company. So our software and our IP is used in a lot of the components you are seeing around here and a lot of your phones, and I'll show you how here in a minute how this then also applies to the aerospace domain. So if you look into electronics, this is all about the electronic part of the system originally, but now this also connects into the electromechanical pieces, as I'll talk about a little bit later. If you look into here what happened in the 60s with the original digitalization with semiconductors and systems, the way that has developed at this point, you have cloud, 5G, specialized chips, you have artificial intelligence getting into our lives. My phone, when I wake up, already knows that my train is late and alerts me and so forth. We are on the design side. So in the 60s, the EDA, the electronic design automation industry, was essentially doing manual layout and we started automating these things. And today we're using, just like these tools, like the applications, we're using parallelism, we're using full flow solutions which allow you to automate a lot of the designs, and then we're using deep learning and artificial intelligence in our tools. So what does that have to do with the aerospace area which we have here at the Airshow? So if you look into the F-35, that's a Joint Strike Fighter, that's a Lightning II, it's really what we refer to as a systems of systems. What we mean by systems of systems is hardware and software. Just the top level for the cockpit is giving you 8.3 million lines of code according to the statistics, and that doesn't even count all the embedded software and all the subsystems in the different subsystems going into the strike fighter. Very, very complex interactions between all the systems. You really need multi-domain expertise. So you need to bring together the electronics with the mechanical and with the whole environment you're dealing with. So where does, how does the stack look like? How does the different components look like? If I go in here and I just pick this as a conceptual example, if I then go into a subsystem, like in this case a communication system with two-way IP communications from the plane to the ground, at the end you have these subsystems, and you have hundreds of those obviously in something like the F-35, and then into those you bring chips. So this is a system on chip with complex software on it. This is the software I mentioned earlier, which is kind of hidden. And then you have the system integration, and all of this goes into the plane. The way this then is designed, I'm often using an analogy here of different levels of abstraction. The complexity of the plane is kind of like me standing on Mount Hamilton in the Bay Area and trying to design top-down the Bay Area. So I have to figure out, oh, there's San Francisco up there, San Jose, here's Santa Clara. If the ice hockey game is over, I need multiple buses, multiple transfer mechanisms to go across. So I have system architecture effects happening at that high level, and then I refine further all the way down to the chip and IP level, going into those subsystems in the airplane. So where does Cadence fit into all this from an electronics perspective? So you have the stack, then you have building blocks. So those are like Lego blocks. You can see at our booth, for example, the vision processor building blocks. our company provides, which go into subsystems, go into the chip, go into the board, which then goes into the actual hardware, and there's lots of software layered on top of that as well. And this is only the chip which goes into the subsystem. All this now repeats as we put this all into a more complex system. The way we fit into this, you have design IP, we have the Lego blocks, which help you to assemble the chip. We allow you to create the data to implement the chip. We allow you to verify the chips and the environment with software. There's board design in there, and all of this then connects up here into the space of software that executes on top of this, the hardware stack. So you have the hardware stack and the software stack here. So this is where Cadence and the electronic design automation space fits into all this. And this is just the lower building block here. Cadence as a company then expands into what we call intelligent system design, which goes across application domains. So we play a lot in cloud data centers, in mobile, IoT, industrial, automotive, and of course aerospace. Here, that's why we're here. And it's a core chip development going into the system analysis, the embedded software enablement, and from here into everything smart, the pervasive intelligence into our tools, and then enabling with our tools to build chips and systems in that domain. So Cadence at a glance, as a company, given that until today, I would bet a lot of you may not have heard of us, even though we are in the midst of the enablement of those systems. We are at about 2.1 billion revenue in 2018. We had about 577 million in the first quarter, and this is one important characteristic for our industry. It's very research intensive. So we are investing about 42% of our revenue into R&D. So it's a very research intensive industry. So I'll talk about three areas here. The first one is the verification and software development for the chip and subsystem perspective. And I'll use a related example here. We don't have any cars here. Everything is flying and doing pirouettes here in the sky over Paris. But if I look into the vehicle, into the car, it has a very similar structure of design sheet. From the processor into the microcontroller, into the subsystem, into the actual car. And you have a very complex set of interactions between the hardware and software developers and between the OEMs and their suppliers. Just like here, these chalets out there are essentially typically these the equivalent of the OEMs, and a lot of the companies in here are the suppliers into that domain. So the semiconductor focus where we came from as Cadence and electronic design automation is typically focused on those lower levels, but is going up into enabling full systems. So what do we do about this? We have this V diagram which is used across a lot of those industries, from requirements through system design, subsystem design, specifying some of the components in the chip, and then just the chip development itself may take 1.5 to 2 years, right? So now take that chip development and make it part of the system integration as you walk up the V diagram again. And what we're trying to do in our industry is to really shift left and integrate virtually the systems as you come down on the requirement side, integrate it and get the integration done much earlier. So let's double click on this side of the actual chip development. So if I go back to my chip, which is at the bottom end of a subsystem, you have your IP, your processor, subsystem, SoCs, and it may take you 18 months to 2 years to actually have the chip ready. So what's interesting here, for this chip to be essentially ready, because I can change it once I'm in the final chip stages in the production and post-silicon bring up, I really need to have all the hardware software keys sorted out here. Which is only about 60% throughout the project. So traditionally, what people are doing my colleague James Chu here, who's driving a lot of our aerospace activities, always refers to this as the fly fix fly loop. So you build something and then you try it, and if it doesn't work, well, you have to rebuild it, redevelop and fix it and try again. Which is the equivalent here of saying we wait until we have the chip to have the software and do the software development on top of it. So what we're doing as an industry, we're moving this all left into the virtual space and allow continuous integration of hardware and software throughout the design cycle for chips and subsystems. And the interesting part is there are several tools around several kind of development environments, from something we call System C, RTL, that's a language with VHDL actually originally developed by the likes of DARPA. That goes into emulators, prototyping systems. You get first silicon and your board. So you have many different development techniques throughout the process, and that's just your chip and your subsystem. This now extends further into connections to the electromechanical world, for example. The interesting thing here is you have lots of different requirements throughout the design flow. In order to do software development here, you need things to be available early. You need it fast and accurate. You need to have limited investment into developing it. The application needs to be easy. You need to be able to debug it. All of these are not necessarily all aligned. There's actually no tool in the world which can do all of these things equally good, except, given that I have a German accent, even though I'm living for the last 21 years in the US, in Germany we actually have that thing. We call it the eierlegende Wollmilchsau. It's a piece of an animal which can lay eggs, give you the wool, give out milk, and also gives you the bacon at the end of the day. And it produces all the daily necessities. Well, of course that's a fable in Germany too, and there's really no engine from the pure virtual to the actual chip and the actual prototype around, which gives you all the characteristics at once. So the virtual platforms are available early, they are less accurate. Once you get accurate, they get the Verilog and VHDL simulation gets slower. You have limited software debug on it. When you get data into the design floor, you have faster execution, but you have some modifications and it's harder to replicate. Here it's late in the flow, very late in the flow here, so you need to have a combination of these techniques to develop your hardware software system, and that's really what some of our tools are about. So those are virtual platforms, prototyping systems, and emulation, which allow you to emulate your chip and your subsystem before you produce it. So this is the emulate before you fabricate type of tagline we are using, and this allows you to find the bugs in the design throughout the design flow much earlier, and it gives you this what we call shift left, the early integration of hardware and software earlier in the design flow. For example, NVIDIA is one of our big customers in the commercial world. They're doing their graphics chips like that. There's a blog out here about their emulation lab, a couple of videos too, how they really, this emulation before fabrication, bring hardware and software development together early. And this extends into the aerospace as well. So Northrop Grumman, in this case the military aerospace, here's a press release from very recently, earlier this year, where we are collaborating with them on chip design and subsystem design. So what do you do with this now, going back from our chip into the subsystem, into the subsystem of the plane and the full plane? Well, this whole notion of emulation before fabrication in this case is done and is achieved by bringing together virtualized nodes which represent things which may not exist as chip yet or are still conceptual, and combining those with some of the components for which we have actually all the information available to actually emulate them and to actually run them in execution. So with that, a mixed level environment can be set up for hardware-software development to enable the verification of systems. We recently announced in this domain a new breakthrough with our Proteon X1 platform, which has much more scalable capacity and performance and still very fast bring up coming from our emulation system. So emulation and prototyping go hand in hand together. So this is the digital part. Let's talk a little bit about the physics and reliability part. So if you look at the electronics from the chip through the package, through the board, into the full system, maybe a car, maybe a plane, you have to really figure out how to do performance throughout those, how to do this compute and performance of communication between those components at all levels of abstraction. So you need to do this electromagnetic, thermal, optical, mechanical. You need to take into account safety, security, and quality. So in this space, we have various simulation tools available from the transistor level. We can deal with transistor aging, migration, through the package level, how the chip actually behaves in the package, through things like thermal dynamics happening on the board. That's then integrated into the subsystem, the control unit, and that then actually goes into a communication where you have the network level of those items being connected. So the basic takeaway here at all levels of abstraction implementation, you need to be able to do the physics simulation and deal with reliability at all those levels. And that's an area where we are moving into. We recently announced a new product called Clarity, which is really for 3D solving, the electromagnetic extraction and simulation, which has much bigger performance while maintaining accuracy than was previously possible. So this is using parallelization quite heavily. So with that, you can go into a car or into a plane, and you can do 3D solving, dealing with electrical field issues for the board, the connector, and the cable, to really analyze the electromechanicals and the 3D solving effects in your design. And that extends to things like RF, where you can do RFIC co-design environment with our Virtuoso solution. We have a single golden schematic, which is used for implementation, verification, and the electromagnetic analysis. So this is now going way beyond the pure digital hardware software that I mentioned earlier. So those are simulation tools which enable the electronics development, eventually going up to the systems of systems level of planes. So one of the cool buzzwords, but it's really in my mind not something that's going away, is what people call digital twins. So if I have my real system around, my real plane around, what happens is I have this situation that data is really at the center of everything. I have devices like my HoloLens over at Microsoft, my plane, my car, my phone, my little handy helping robot, creating data in unimaginable large volumes. So you create data, they need to be processed in data centers. There's big discussion going on. Where do I actually compute the data? Do I compute them more at the end nodes? Do I compute them more in the cloud? I need to deliver all this data and with wireless and wired infrastructure do the transmission of the data, and I need to store it. So data is at the heart of everything here, creating, processing, transmission, and data storage. And in that context, you have AI, the machine learning and artificial intelligence pieces, where we are playing heavily. It's what we call AI Inside. That's making our tools more efficient. So that's making the designer productivity more efficient, bringing them flows that weren't available before. So a good example here is Just to put it into layman's word, if I have a Tesla and I have it fully automated, that gives me now new ways of using my Tesla. I can now build my farm and my fleet of 20 Teslas and start a new method with my car and basically be my own rental service. And then there's enablement, the hardware software co-design, which I mentioned earlier, which is used in big AI chips, and also the IP, the Tensilica IP, for example, with the DNA 100, our latest processor, enabling machine learning. Here's an example of a company which has recently deployed some of our tools to Synkai. They're providing machine learning and AI solution, SoCs, platforms, and software. So they use our verification tools, which I mentioned earlier, the verification environment, to do the system and software development for those chips. So with AI, humongous amounts of data, or as my 14-year-old daughter would say, ginormous amounts of data. What do I do with them? Well, one of the things these data are used for is what we call digital twins. What's a digital twin? It's a digital representation of the current state of a manufactured product at any given point in time. So as I'm driving my product development, I have different sample points of digital representations as I'm developing it. And even then, when it's flying, driving, or moving around, I want to be able to use that data and reuse it in the digital twin to make predictions. I'll go into that in a minute again. A digital thread is then the record of all states. So this would be the last 250 flights of an airplane, of a car, or of anything where the data is created, which captures all the states of the manufactured product or system from conception to disposal. So I really want to now take my data from my plane, apply it to my digital twin representations, and then drive that towards predictions when my next part will fail, for example, based on the machine learning around how the system behaves. So there's a subset here of digital twins which we are using for verification. There's actually this flow I showed you earlier from the virtual world through different snapshots of the system as it's under development. So we think about the digital twin as a subset of all this, as a functional, correct, predictable, and reproducible representation of the product. So as I'm developing my system and as I'm defining it, I have different snapshots where I can go back later on in the implementation where I may find a defect and apply this defect later on the front again. This is what this shows here. As I'm defining my system into subsystems and driving through the development flow, I can actually take data, experience data with machine learning to optimize how my implementation looks like. And then going backwards, I'm taking the actual data sets and apply them to the earlier representation. So you can, for example, take real-life data and apply it to a digital twin to check for defects. You can front-load your analysis to reduce issues. You can apply real-life data to tune performance. So it's one of the examples I had in a previous life in automotive, where we had essentially digital twin for car effects. One of the things our customers were worried about, they really didn't want to expose the test pilots and the test drivers to the very extreme cases which the hardware needed to be validated for. So they did this virtually first in the digital twin to see how the digital twin would behave. And then as you now take this digital thread and have states throughout the life cycle, you can use this with machine learning to predict maintenance issues, for example. With things like the prototyping here, you can figure out which is essentially a digital twin of the actual chip and subsystem later on. You can predict things like how software loads have to be changed over time, and you can monitor the impact of mechanical wear, reliability analysis, and front load that. So as I mentioned earlier, as I have this board, I mentioned the physical simulation pieces up here. So with real life data, I can figure out my reliability early on in the cycle, applying it back to tools like Clarity and Virtuoso I mentioned earlier. So that's what digital twins are about. I'm personally very excited about them. So one of my favorite movie references here is, sometimes I don't know, most of the time I'm 99% excited and 1% scared. There are days where I wake up and I'm only 1% excited and 99% scared. I'm not sure who gets the movie reference, but it is Armageddon. So these digital twins here, this is, assume you have a virtual record of yourself, and you have that virtual record applying AI to yourself. So kind of like my phone today at the smallest level learns about what I'm doing in the morning, and it kind of gives me the weather and the news of my favorite channel right away today. That will grow, that my digital representation of myself may know, oh, I didn't sleep that well because my Fitbit transmitted all the data already. So it gives me the hangover cure in the morning and recommends that, right? The challenge we have with those digital twins, and this is obviously a fun example more on a personal level, but when I have these neural networks which are trained with data from data sets to see how I behave or how the brain behaves in an environment, we actually don't fully understand today what those numbers in the neural network mean. So actually to verify that the trained neural network can do something bad or can't find an exception I didn't think about and react wrongly, it's something we as an industry need to deal with. We need to deal with security and safety issues. There's a question at the end, who owns the data? There's new ways to really communicate between the digital version and the real version. So you can reproduce the data of the real version in the digital twin. And then at the end, you need to be able to deal with multi-domain execution. So to me, I would say most of the days it's 99% exciting, but when you think through it, it can be pretty scary if such a digital twin is potentially going wrong. A couple of minutes for questions. I'm at about the half-hour mark. So this notion we have at Cadence called intelligent system design goes really from the chip through the package with design verification, implementation, the IP blocks going into it. You can see some of those at our booth. The services we provide, it's going into the control unit level design, the subsystem design, where you can do prototyping, you can deal with signal integrity, power integrity, thermal integrity, electromagnetic integrity, and then that goes into the system and systems of system level where you have network modeling, you deal with KiCad, MCAD, co-design, the electrical and the mechanical, the EMI co-design, and you can simulate physical channels. Bottom line, we can simulate pretty much everything, which allows you to build these digital twins where you can then reapply the data from the real world to your digital twin data. So this is the physics at all levels, the system functionality with hardware and software. Before you fabricate, you can run this on emulators and prototypes. You can deal with reliability, safety, and security early on. We can do this alone. We have lots of partners in the industry. Here's just one, given that this is a very safety and security sensitive crowd. One of the companies we're strategically partnering with is Greenhouse, where it's in the embedded safety and security market, and it's really furthering our already charted paths of intelligent system design, moving up the system stack, adding to our emulation and prototype, emulate and prototype before we fabricate, and safe and secure software on top of it. All of this happens in the cloud as well. That's very important for this environment as well. You can have this in your own cloud environment, you can have it in commercial cloud environment, you can have us that manage the cloud for you. So there are different ways to interact in the cloud with us. And last slide to leave you with, this is the notion we call intelligent system design, cloud enabled, coming from the digital and analog verification with IP being integrated through system analysis. I mentioned therapy, but also the embedded software parts, the embedded software development and verification, including security aspects. All that moves into what we call pervasive intelligence, where you have machine learning everywhere, optimizing our tools, doing new flows, and then enabling for our customers the machine learning across all of the application units. With that, I'll open it up for questions. So we are just about 100 meters, yards, and that's like how many foot? 300 feet down the road here on this side. So if you want to see more about the vision parts, the digital analytics, and some of the digital twinning I mentioned, please visit us. Thanks for having us.